In the previous video, we discussed about the JK flip-flop and its logical diagram and what are the input combinations possible and how the output variations is taking place and its timing diagram. Now, in this video, we are going to discuss one problem related to the JK flip-flop and how we can overcome that problem. So this is the truth table for the JK flip-flop as shown in the slide. So in this we are going to concentrate on this combination of the inputs, that is 1 1. So when j is equal to 1 and k is equal to 1, we know that we will get a toggle condition as the output state. That means whatever be the previous state, its complementary will be the current state. Now, one of the problem related to this is going to discuss in this video. Now, the slide, the timing diagram for JK flip-flop is shown. This is signal applied to the J, this is a signal applied to the K terminal, and this is the clock signal, and this is the output. Now, before applying the clock, that is, before applying this clock, your output is 1. So, when the clock is applied, J is equal to 0, K is equal to 0, so your output will remain as the previous state, because 0, 0 means there is no change in the state. Now, in this region, even though your inputs J and K are changing, but your output will remain as the previous state because there is no clock signal. Now, when next clock pulse comes, so you can see that J is equal to 1 and K is equal to 1. When J is equal to 1 and K is equal to 1, your output Qn plus 1 is equal to Q complement. That is, whatever be the previous state, its complement will be the current state. Now, there is one problem with this. That is, here you can see that this is the clock signal width. This is the width of the clock signal. That means during this entire period, your clock signal is high. Now, during this entire clock signal, you can see that your J is equal to 1 and K is equal to 1. So, when you apply the clock signal and J is equal to 1 and K is equal to 1, you will get the complementary of the previous state. So here the previous state is 1, so it will change to 0. Now the state is changed to 0. Now even though the output is changed to 0, still you have the clock signal. You have the clock signal and you have the input as 1 and 1. That means currently your output, initially your output is Qn plus 1 changed from 1 1 to 0. Now your output is 0 and your clock signal is there and it is 1 1. So what happens? Again your output will get toggled. That means it will change from 0 to 1. 0 to 1. So this toggling will continue till the clock signal is removed. So here what happens is that your clock signal width is greater than the propagation delay. Propagation delay means when you give the input, what is the time required to change the output. So when your propagation delay is less than the clock signal width, your input is given as the 1 1. So your output goes on changing. That is, you cannot predict what will be the final output. That means when you remove the clock signal, what is the output? Because this toggling continues. So this is known as the race around condition. That means your output will get toggled more than once when you apply J is equal to 1 and K is equal to 1 and your clock signal. So this is known as the race around condition. Now, to overcome the race around condition in JK flip flop, we are using a master slave JK flip flop. So, in master slave JK flip flop, as the name indicates, we have one master JK flip flop and one slave JK flip flop. Here you can see that two flip flops are there, and the clock signal applied to the master, we are directly applying the clock signal to the master flip flop, and the clock signal that we apply to the slave JK flip flop is the complementary of the master flip flop. That means if if the clock signal is becoming high, then a high signal will be appear here and a low signal will be appear here. That means the output will change only for the master flip-flop. The slave JK flip-flop will not change because you will get a 0 as the clock signal. Similarly, when the clock signal is 0 here, that is for a master flip-flop, when the clock signal is 0, the clock signal of your slave will become 1. That means at that time your master flip-flop will not change, your slave flip-flop alone will change. So at a time only one flip-flop is working, and the output of the slave flip-flop is fed back as the input of your JK flip-flop, and similarly the output of master is used as the input of your slave. So this is the master slave JK flip-flop combination. This is the logical diagram of your master slave JK flip-flop. So here you have the master part, here this is the slave part. Now we can consider j is equal to 1 and k is equal to 1 and clock is equal to 1. So this clock here you will get as 0. That means this will be 0. So when the positive part of the clock comes, a 1 will be appear at the NAND gate of N1 and N2, and a 0 will be appear as the input of N5 and N6. For simplicity, we can consider Q is equal to 1 as the previous state and Q bar as 0. Now, if you take the NAND gate N1, we have three input. First one is 1, that is from the clock signal. Second one is 1, and the third one is 0, that is from Q bar. Now, if you take N2, you have 1, 1, and the third one is again 1. So if you take N1, inputs are 1, 1, 0, so its complement it will be 1, and for N2 it will be 1 dot 1 dot 1, its complement it is equal to 0. So the output of NAND gate N1 is 1 and the output of NAND gate N2 is equal to 0. Now if you take NAND gate N3, so one of the input is 1, the second input is M2. So this is M2. So its complement that is equal to M2 complement. Now this is fed back as the input, that is this will be M2 complement. So that will be fed back as the input of N4. So if you take N4, one of the input is 0, the second input is M2 complement, its complement 0 dot M2, that is 0, and its complement it is equal to 1. So the output of N4 will become equal to 1. That means M2 is equal to 1. So when M2 is equal to 1, M2 complement is equal to 0. That means the output of N3 will be equal to 0 and the output of N4 will be equal to 1. Now if you take N5, this is 0, one of the input is 0, so the output will be 1. Similarly for N6 also, one of the input is 1, one of the input is 0, and so the output is 1. Now here the Q bar, it is equal to 0, so the output of N7 will be 1 dot 0 its complement, that is equal to 1, and this is 1, so 1 dot, that is for N8 1 dot 1, so it is 0. That means M1 gets changed. So when the positive clock is coming, M1 changed to 0 and M2 is equal to 1. Q is equal to 1 and Q bar equal to 0 at that instant. Now we can check whatever happens to the circuit when the negative clock comes. Now when the negative clock is coming, that is, this will be 0, so this will be 1. So this will be 1. Okay. So if you take NAND gate N1, one of the input is 0, that means the output will be 1. Now if you take NAND gate N2, one of the input is 0, so the output is again 1. So the NAND gate N1 output is 1 and N2 is again 1. Now if you take NAND gate N3, one of the input is 1, the second input is again 1, so 1 dot 1, it will remains as 0, so this will be 0. This 0 is getting fed back as the input of N4, so the output will be 0 dot 0, its complement, it is equal to 1. That means M1 will be equal to N1 is 1, N2 output is 1, M1 output is 0, M2 output is 1. Now if you take N5, one of the input is 0, the second input is 1. One of the input is 0, the second input is 1. So the output will be 0 dot 1, that is 0, its complement is equal to 1. Now if you take N6, both inputs are 1, so the output will become 0. So N5 is 1 and 6 is 0. Now if you take N7, that is NAND gate 7, one of the input is 1, the second input is 0. So 1 dot 0, this will be 1. So this is 1. This 1 is getting fed back as the input of N8. So 1 dot 0. Now this is 1, this is 0. So 1 dot 0 means this will become 1. So this is 1. So this 1 is getting fed back as the input of N7. So this 1. So both inputs are becoming 1 for N7 now. So the output of N7 will become 0. So this 0 is getting again fed back as the input of N8. Now the input of N8 will become as a 0. Both inputs are 0, so the output will be 1. So this again fed back to the N7. Again the N7 output is 0. So this is a stable state. So this at the stable state you will get N7 as 0 and N8 as 1. So final, that is Q will become equal to 0 and Q bar will become equal to 1. That means you will get the complementary of the previous output. Now this 1 and 0 again fed back to the N1 and N2. This will become 1 and this will become 0. But N1 output will not be changing because one of the input is 0. Similarly, N2 output will not change because one of the input is still remains as a 0. So this is a stable condition for the flip-flop. Now from this we can understand that During the positive half cycle of the, or when the clock signal becomes high, your master part will only work. So during the positive clock signal, your master part will work. Now, for the negative signal, only the slave part will work. So during the positive clock signal, the master part will change according to the your input combination. That is, it is changing according to the input combination. Now that output is transferred as the output of your slave part. So this is how your master slave flip-flop is working. So this is the diamond diagram for the master slave flip-flop. So your master will work during the positive edge of your clock signal, and your slave will work during the negative edge of your clock signal. Now when the positive edge of the clock signal is coming, you can see that J and K, whatever be the value of J and K, according to that your master output will change. Now this master output change will be transferred to the slave during the next negative edge. So here you can see that we can take this instance. So when the clock signal is becoming, or when the positive edge is coming here, you can see that your J is equal to 1 and K is equal to 0. When 1 0 occurs, your master will change, or master will set. The master flip-flop will set. So this becomes 1. Now during the next, that is the next negative edge is coming, this master output will be transferred to the slave output. That is your final output. So this is happening in master slave JK flip-flop.